Now we're going to look at a work problem in which we're pumping water to the top of a circular cylindrical tank, and we want to see how much total work that's going to require. Now I didn't add this in, but it's important for this problem. We need to know that water weighs 62.5 pounds per cubic foot. So what's the situation? So the question is, how much work does it take to pump the water from an upright and full right circular cylindrical tank of radius 5 and height of 10 to a level 4 feet above the top of the tank? Alright, so first of all, this is a cylindrical tank whose radius is 5. So that's a 5. We know that the height is 10 feet. And we're up here, so our pump is like up here somewhere. It's a terrible pump, but whatever. And this distance here is 4 feet. This distance above, between the top of the tank and where that pump is, accumulating the water. And so this tank is full, and we're trying to lift the water, all the water from the bottom all the way to the top. We're lifting it all the way up to 4 feet. And so this is clearly a calculus problem, because there's a continual and gradual change in both the distance you're lifting the water up and the amount of water that's left in the tank. Right? These things are all varying, and not in a discrete way. So how do you analyze something like this? Well, the thing to do, like in most calculus problems, is to analyze some arbitrary section. So for instance, I'm gonna imagine what it takes to lift one arbitrary slab of water. And what I mean by slab is almost like a disc that I have drawn here. So let's pretend we're trying to lift just that disc of water. So work to lift one slab of water. Well, we need some variables in here. So in this picture, how high would we be lifting this slab of water? Well, let's just assume that this slab of water is, let's say that's y units above the ground. Well, I'm going to have to be lifting this distance right here. So how do I describe that distance? Well, the distance from the ground all the way to there is 14, and if this section is y at the bottom, I got to call this 14 minus y. So I'm lifting that 14 minus y feet. So there's my distance. Now what I need is the weight. So what's the weight of this slab of water? Well, let's see. It's made of water. And we know that water weighs 62.5 pounds per cubic foot. But I don't know how many cubic feet I have here in this slab of water. So let's actually figure that out. So I'm going to call this, there's my radius, that's 5. This is a small change in y, so that's dy. So the volume of this slab is going to be pi r squared times dy. Or in other words, 25 pi dy cubic feet. So that's the volume of the slab. And so then the weight is going to equal the volume, 25 pi dy, feet cubed. I'm just doing the units so you'll see them cancel, times the weight of water, which is 62.5 pounds per cubic foot. And those go, and you can now see that our units are going to be pounds, which is, we can view that as a force. So now we know that our weight, or force, is equal to, let's write this all out together. 62.5 times 25 turns out to be 1562.5 pi dy, pounds. All right, so I'm all set now for the weight of the water, but work. So that's like my force. That's my force, right? Now to do work, you have to apply force over a certain distance. So we're lifting that slab of water which has that weight, and we're lifting it 14 minus y feet. So our work, I'm going to write as force times distance. So that's 1562.5 pi. I'm going to put the dy at the end. I know it's there, but I'm just to make it look better. Times the distance, which is 14 minus y, as we saw up here in the picture. All right. So again, there's my so I've got force times distance here, and that is just the work required to lift that one slab. Now, obviously, that's just the one slab. We want to be lifting up these slabs as y goes from 0, meaning you're lifting the very bottom slab, all the way up to the very top slab, which is when y is 10. So we're going to say the total work is going to be the integral. So we're going to add up. So I'll do the limits of integration again. I think that confuses some kids. But let's just put in our work, or our force times distance expression. All right, so there's my my integral getting set up. And again, the bottom slab will be lifted when y is 0, and the very top slab will be lifted when y is 10. And so now we have an integral, and we just need to punch this into the calculator. Now I can already anticipate a question that some students will have. The first question they'll ask, or historically they'd ask, would be, how come this doesn't go up to 14? And the reason it doesn't is because, remember, we're lifting up the slabs of water, and that's what the limits of integration are tracking. So when y is 0, that's this bottom slab of, the bottom slab of water. The top slab of water is going to be when y is equal to 10, and you still have to lift that top slab of water 4 feet. So if you imagine putting a 10 in here, you can see that you would still have to lift a distance of 4 feet, which is going to be the shortest distance you'll need to lift the water. The second question students ask me is, how come we couldn't just put this force expression right into the integral, like we did in the last problem, or in the problems earlier where you're just putting a force function into the integral? And the reason is because in this case, the differential here, the differential dy is included in the weight or the force expression. In the basic integral before, you had force, and the dx was actually your taking care of the units of distance. But here, that dy is not part of the units for distance, so we need another expression to account for distance, and that's where this 14 minus y comes in. So, in any case, when you put this in the calculator, you end up getting 441,786, and that's foot-pounds. So kind of a complicated problem if you think about it, but really it's important to just analyze one slab, figure out the work needed to be done on that, and then you integrate with respect to the height of the or with respect to the distance from the bottom of the tank to the slab, and you should be good to go.